This is the first video of a new playlist, which is called Video Papers. It is a playlist where I present my own papers, the research papers that I publish regularly on typically very technical work. These presentations are not meant for a wide public, but only for people who are interested in these papers and want to have a help in reading them by listening to a video where the contents are explained, I hope, quite exhaustively and clearly. So in this talk I begin from my recent paper, which is entitled A New Quantization Principle from a Minimally Non-Time Ordered Product. Let me explain what it is about. The search of new physics beyond the standard model can proceed in two ways. One is by assuming the existence of new particles, symmetry groups, or new interactions, and that means that we use the same ingredients that have worked so far for the standard model and the other theories, possibly arranged in new ways or with various variants, but we are not going to modify the fundamentals of quantum field theory. The second approach is to tweak the fundamental assumptions of quantum field theory, renounce some basic principles, hopefully in the most conservative way, because otherwise we have too much arbitrariness, and see what we can do there. The first option can be good for a lot of phenomenology, and it is the one that is mostly pursued by phenomenologists today. However, it cannot reach quantum gravity. That we know already. The second option is the only possibility we have for quantum gravity, if we remain within the realm of quantum field theory. That is to say, we are not going to throw quantum field theory under the bus for loop quantum gravity, holography, for string theory. We just take what has been so successful so far, quantum field theory, and make a further step. In that case, we have to tweak the fundamental assumptions, because otherwise we are stuck with the problems that have been challenging for the past decades and that have never been solved. And in particular, in quantum gravity, the basic problem is to make renormalizability compatible with unitarity. This second approach could also be useful for beyond the standard model phenomenology, but it is mainly thought for quantum gravity. So in this talk we will consider the second option. Before plunging into what's new here, it's convenient to summarize what's old. The old quantization principle. What do we do in quantum field theory when we want to formulate a theory? So normally the quantization of perturbative quantum field theory starts from a classical Lagrangian. And then the classical Lagrangian is separated into the sum of a free part and an interaction part. The free part provides the so-called propagators, which are time-ordered, that is to say, they are defined by means of the Feynman I epsilon prescription. The interaction part provides the vertices. Then one builds Feynman diagrams, according to the formula written here, which is the S matrix. You see the time-ordered product and an exponential of the interaction Hamiltonian. The S matrix will be split into the sum of two terms. One is the identity, where nothing happens, and V is the amplitude. We will call it amplitude. Normally it is written as IT, but to save some I factors here and there, we will incorporate this I into the definition of V. What is the motivation for a new quantization principle? Well, in many cases, for example, we can have that theories with fields that have negative kinetic terms in the free field limit, or that happens with higher derivative theories. In those cases, the S matrix that we build in the way we have just described is not unitary. That means that it does not satisfy the identities that are written here, S dagger S equal 1. If you decompose S as usual, 1 plus IT, that identity can be written in this form, which is also known as optical theory. Now, it would be nice to have these identities, because these are crucial for a fundamental quantum field theory. But it's not possible to prove them with the usual framework if you have fields which have free negative kinetic terms. So what do you do? Luckily, in these cases, the S matrix built with the usual procedure satisfies a different identity, which is called pseudo-unitarity equation, which is still very useful, although it is not the good one. This is the identity, and you see that on the right hand side between T dagger and T you do not have the identity, but you have C, a matrix which is diagonal with eigenvalues +1, -1 and possibly 0. Now 0 is not particularly important because you can get rid of it. It means that there are auxiliary fields. What is important is that there are some positive and some negative eigenvalues, and the negative eigenvalues signal the presence of ghosts. And so these are violations of unitarity. What to do in these cases? Well, normally you stop there, because the usual quantization principle leads to this result, and discard the theory. The theory does not make physical sense. But is this the right thing to do? Discard the theory. Let's clarify what our goal is here. We would like to take this equation, which is the non-satisfactory one, and project away the wrong part. So we have said that IT minus IT dagger is equal to minus T dagger CT, and C is a diagonal matrix with 1s and -1s in the diagonal, and you would like to get rid of the -1s, of course, because those signal the presence of ghosts. In particular, if you insert in and out states, you have an identity for amplitudes. This is the amplitude. Here you have conjugate amplitude, and on the right hand side you have a certain sum where you have amplitudes and conjugate amplitudes multiplied by minus signs or plus signs depending. Now the point is that if you want to get rid of something, it's easy to ignore states like the ghosts you do not want from the in and out sets of states. So in and out is something you can choose. You can put anything you want there, and you cannot put anything you want. So that means that you are only considering certain processes where the initial particles are the ones you want, and the outgoing particles are the ones you want to consider. You discard everything else and hope that physics will match this choice, namely that in physics, in reality, only what you consider is happening. The point is that you cannot decide by yourselves what appears in this sum inside. So while you can always make the projection you want for free in the choices of in and out states, there is no way to make this arbitrary choice about the sum appearing in between. You have to take what you get. So the problem of projecting out the undesirable states is non-trivial. We need a consistent mechanism to assure that a removal from the in and out implies an analogous removal from the inside. And this is absolutely not easy to gain. But there is an example where it is known how to get it. These are the Faddeev-Popov ghosts and the unphysical components of the gauge fields. And there you have a mechanism that ensures the consistency, which is based on the Slavnov-Taylor-Ward-Takahashi identities, and they are implied by the gauge symmetry. But what if we do not have a gauge symmetry that can help us? Then you need to change the inside of every diagram, because here no miracle will occur otherwise. So, to repeat, in gauge theories, if you do not want Faddeev-Popov ghosts from in and out states, and the anti-ghosts, and the temporal components of gauge fields, and the longitudinal components of gauge fields, you just don't want them. You are free to discard them from the sets of in and out states because this is your choice, but you need something to guarantee you that when you do that, they automatically disappear by some sort of miracle from the sum of inside states here. Then you have unitarity in the subspace you are considering, because in that subspace you will only have plus signs here, and C, this matrix C, will be equal to the identity in the subspace. So gauge symmetry is the basic tool that allows to prove this, but without a gauge symmetry you need to change what's inside the diagrams, because otherwise this will not happen. And what's inside the diagrams is the very definition of diagram. So you need to use new diagrams. So the new quantization principle that I formulated in this paper works as follows. First of all, you have to say that the quantization does not end with the usual S matrix. What you get with the usual S matrix is just an interim scattering matrix, and that is the starting point of a more elaborate quantization principle, quantization procedure that continues. And you need to do some further operations. You need to reach the physical scattering matrix. What to do? What are the possibilities to build a physical scattering matrix as physical that is unitary in a subspace, which we will call physical subspace, of the total Fock space, out of an ordinary scattering matrix that is only pseudo-unitary, or maybe it is unitary by itself, but we want anyway to make the projection to some subspace. So this is a problem of projection of the unitary or pseudo-unitary scattering matrix that you obtain from the usual procedure onto another unitary scattering matrix or onto a unitary scattering matrix. So for convenience, we write, as we have just said, S equals 1 plus V, and we work with the matrix V, so we subtract the identity from the S matrix as usual, and this matrix V will be called amplitude, although it is not what is used normally in the usual terminology. We want to build a unitary amplitude from a pseudo-unitary one. First, we just do a simple exercise with matrices. Assume that A and B are two Hermitian matrices, and V is a matrix that satisfies the equation that you see here. then the most general solution of the equation you see here below is what? It is given in the formula you see here, which is quite complicated apparently, but anyway, it is a formula where you build the new amplitude out of the old amplitude. The matrices A and B that we have assumed as starting points, and a new matrix omega, which is arbitrary at this point. And then you apply this complicated formula that we will study in detail, because this is the formula that encodes the new diagrammatic rules. Omega is an arbitrary anti-Hermitian matrix. So this is the situation. This is a problem with matrices, and below you find the solution. The solution is this one. Now, in the set of solutions, there is a very, very simple solution, which is the one with omega equals 0, where you lose the whole part here. And the solution becomes very simple. You would hope that this is the right one to save a lot of effort. Unfortunately, it has many undesirable properties. And so omega cannot be 0. We will see what happens when you do not insert this option to introduce an omega. But we will start from the simplest solution because it is simpler. When we have this theorem, now that we have this theorem, what can we do with it? Well, if V is the usual amplitude that satisfies this equation, and C is a matrix that has ones and minus ones or zeros in the diagonal, and it is a diagonal matrix, then you choose A, one of the matrices that we saw before, A and B. A will be a projector onto a certain physical subspace where you pick some ones here out of the matrix C. Not even, you don't need to pick all of them, some ones, and zeros everywhere else. And this you take as the projector onto the physical subspace. So, let me say it again. We start from an equation that is unsatisfactory. And this is provided by our quantum field theory that contains ghosts, for example. We do not want that. So what we have is this identity, V, we have, C, we have. Then, to solve the problem, we choose an A. We then define B equal to the difference C minus A. Then, by the exercise of matrices that we have done before, the formula we have given before solves this equation, which is nothing but unitarity for the physical amplitude that you obtain by projecting. If you put the projector to the left and to the right of this matrix that you obtain by applying the formula we have seen, we'll just have the unitarity equation in the subspace, and that allows you to claim that you have found a unitary amplitude V physical in the subspace W physical. So in that subspace you have a unitary amplitude, and in that subspace you have a unitary S matrix. So far this was an exercise of mathematics, linear algebra. We want to move forward to fields. And so let me denote the set of all fields by big phi, and I split it into two subsets. One is small phi and one is chi. Small phi denotes the field we want to preserve, and chi denotes the ones we want to remove for one reason or another. Maybe they have kinetic terms with the wrong signs, maybe they have kinetic terms with the right signs. we don't ask, don't tell. This is what we want to do. Just split the set of fields into two subsets. One is the subset of fields we want to keep, and the other one is a subset of fields we want, so to speak, to project away. We want to project them away from the physical spectrum. Now, the physical space is then obtained by acting on the vacuum with the creation operators of phi, any number you want. This defines also the projector A onto the physical subspace. The complementary subspace is made of the states where at least one creation operator of chi acts on the vacuum. And this gives the matrix B, which is C minus A. So you have two subspaces. One is a physical subspace, which is obtained by acting on the vacuum only with the creation operators of your physical fields. And then you have a complementary space, which is obtained by acting on the vacuum with at least one creation operator of the unphysical fields, or the fields you want to remove for whatever reason. So basically, A, this matrix, connects only physical legs. B must connect at least one leg that belongs to the set of fields chi we want to remove, at least one. So at this point, we have given the basic rules, and we can start applying the formula to investigate the meaning, in particular clarify the role of omega, and see what we have just said much better, because we have just given the rules, but before seeing examples we cannot really remember what we have said. So we start from the propagators. As usual, the Wick contraction of fields belonging to the physical set is the Feynman propagator. The Wick contraction, the T-ordered product of fields belonging to the set we want to remove, is given by the Feynman propagator, but it could be multiplied by a minus sign. So we have two possibilities here. But then you have also to contract fields that belong to different V's, because in the formula that we have seen before, you have many terms, many. Let's go back and see. When you expand this formula here, you will have V, B, V, B, V, B, V, etc. So what is the product you see here? The product is a product. So inside each V, we know what we have, because these are the diagrams obtained by means of the Feynman rules and the time ordering. But when you contract in between different V's, that is just a product. That's not a time-ordered product. So this is the key point. You need also a second type of propagator, which is non-T ordered. And if you calculate what this is equal to the formula you see here, which is normally called cut propagator. Okay, these are the ingredients. So the complicated formula we saw earlier can be truncated, can be expanded in powers of V and omega, and can be truncated for all the purposes of this talk to the expression you see here, because we will not consider diagrams with more than 4 vertices. 1, 2, 3, 4. Notice that in this formula, V and omega appear on an equal footing. Then you can ask yourself, well, if I fix omega equal minus V, plus something else, for example, I could have 0. I could change the theory completely. And that is true. Using omega, you can change the theory at will. You can even jump from the S matrix of a theory like 5 to the 4th to the S matrix of the standard model. And that is because we have just been playing with matrices so far with no physical input. Sooner or later, we will have to give some physical inputs and restrict the arbitrariness we have on omega. So to avoid this, we require that omega is at least of order v squared, and moreover, it will have to satisfy other properties. So what are products like v, b, v, etc.? We have already explained that these are just products. These means that when you have a field phi from the first v and a field phi from the second v, and you need to Wick contract them, the Wick contraction is the non-time ordered one. Instead, when you have two v's inside the same, two phi's inside the same v, v is in expansion because v is the time-ordered exponential minus 1, then those two are Wick contracted as usual, and as usual means like this. Depending on which set they belong to, they can have plus or minus signs in front. So we'll study various cases, starting from the simplest case we would like to work for all our needs, but unfortunately it doesn't. So omega will be 0. The formula is then very simple, and we will understand why it doesn't work, and we will understand why and what is omega needed for. We simplify things to the maximum. We assume that the particles we have are all physical. We do not want minus signs around because it is easy to insert them when we need. So we just want to get rid of some physical particles and keep some physical particles and reduce a unitary matrix to a unitary matrix in a subspace. So that means that our matrix C we start from is the identity. So we start from a unitary theory. We want to project away, if we project away every field, let's assume that all the fields we want to remove are all the fields. Then the physical subspace is just the vacuum, and that means that this matrix A is just the vacuum, projector onto the vacuum, and then B is 1 minus that. So we start always from this case because it's easier. That means remove every particle from the physical spectrum and see what happens. And we will always start from omega equals 0 to see what happens, and then we will understand that omega equals 0 is not good. After doing that, we will move to omega non-zero, and after doing that, we will consider the case where we do not remove every particle, but we remove some particles. Not only we'll begin with tree diagrams and disconnected diagrams because, surprisingly, they reserve some surprises. Unfortunately, I would say, they are not as straightforward as you wish. And the reason is that you do not have the time ordering any longer. So it's not the same thing to multiply before or after any vertex. You have many possibilities. Then we move to one-loop diagrams from the bubble to the hexagon, and then we study two-loop diagrams, in particular the box with diagonal, and classes of diagrams with arbitrarily many loops. And we will also learn how to descend and ascend in between diagrams uniquely. And in all cases, this is the result we will find, it will always be possible to find a non-trivial omega that matches the results of the theories of physical and purely virtual particles, which I have defined diagrammatically 1 year ago in the paper you see here. So we will match completely the results found there, and those results will be reviewed along with the presentation. So I do not stop here to review that diagrammatics, those diagrammatics rules, but I will make the match between the new results and the old ones along with the discussion. So let's start from the 3 diagrams, and the simplest case is a propagator. We take a very simple interaction Lagrangian with 2 vertices which are linear, and take derivatives, 1 derivative with respect to the first vertex, 1 derivative with respect to the second. If you take the usual amplitude v and you differentiate, you get the time-ordered product. And then in between the 2 vacuum states you have the propagator. Now, the formula for our projected amplitude, the simplest formula is the one at omega equals 0, which we can expand. Well, that formula gives what? So instead of having just v, we have v minus 1/2 vbv plus 1/4 vbvb, but this will not matter in our truncation. This will be enough for the moment. So let's see what happens. And we assume first that we want to project our particle away. So our A is just made of the vacuum, and B is the difference. Well, now we have to differentiate V0, this V0. Basically, there are only 2 pieces here. Not just the usual part, but we get extra terms which are shown here. What are those? Well, we average on the vacuum. If you have a 5 from here to here, we have said that the propagator is not time ordered, so you just copy. You have 2 possibilities because you can exchange x and y, and this is the result. You substitute in momentum space, you find the usual Feynman propagator minus these 2 expressions. They cancel the on-shell part, and you get the Cauchy principal value. You have indeed removed the particle. Careful, because this propagator cannot be used as you see it inside diagram. Inside diagrams, you always have to apply the general formula we have found, and that is what we will do. But the important thing is that we are moving towards theories of purely virtual particles, because you remain with the purely virtual part of the Feynman propagator and you remove completely the on-shell part. So let's move to a simple, more complicated diagram made of 2 propagators. And this time the formula is this. I include the omega correction that is relevant for us. We can truncate the formula here now, but we will see in a moment that omega has to be non-vanishing. Why? Let's ignore omega for the moment and proceed as if we didn't need it. We choose this Lagrangian, differentiate with respect to the sources once for each, and then set the sources to 0. And so you will have what? You will have 2 propagators contracting phi1 with phi1. You have the first propagator contracting phi2 with phi2. You have the second propagator. But then this formula is what? V is the usual diagram. Then you have VBV, which is the diagram, the cut is B. You have 1 cut here, 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 here. And then you have VBVB, which are diagrams with 2 cuts. It is always possible to draw the cuts as vertical lines. You don't have to get mad in drawing cuts, because they are vertical lines and they are the lines that separate the products of V's. Okay, so you draw them all. Here you have to exchange in the permutations. That's why there are some factors 1/2. We find some surprises. The result at omega equals 0 is this. This is the symbol of the diagram. And this is the type of particles I want internally. I would like to have two purely virtual particles. Unfortunately, at omega equals 0, I do not find the expected result from my previous paper, which would be this one. That is to say, the product of the two principal values. But I find a correction which is on shell. These are the corrections. And that's not good. That's where omega enters, because you can add an omega. And remember that omega is arbitrary, but it must be anti-Hermitian. Fortunately, this you can correct with an anti-Hermitian omega. And so if you have a certain omega whose derivatives with respect to the sources is equal to this, and you cancel those two terms, which appear with a minus sign there, then you do find what you expect, in agreement with the previous diagrammatics, and you have completely removed the on-shell contributions. If you want to project away only one particle, you will obtain the correct result, which is the factor, the product between the Cauchy principal value for the purely virtual particle and the Feynman propagator for the physical one, but you still need this omega correction. I skipped the details. When you go to 3 propagators, you have to use the truncation with more terms, okay, and you start getting crazy. Precisely because you do not have time ordering anymore. It's not the same drawing these vertices like this or like that, because time ordering matters with respect to the cuts in particular. Be 1 cut, 2 cuts, and you even have 3 cuts. So these are the diagrams you see here for the vertex, the diagram with 3 propagators with a vertex in common. And here is the diagram with 3 propagators that are adjacent, 3 adjacent propagators. I didn't even list them all because you start needing Mathematica. So let's start with 3 propagators with a vertex in common. If you want to remove the particles from all the internal legs at omega equals 0, you find this. This is the unwanted part, and you can get the correct part, the correct contribution, the product of the 3 principal values after the omega correction as usual. If you project only the first 2 legs, you get what you want. The first 2 legs are principal values, then Feynman, but this time you find another surprise. Not only you get something you don't want, but you also get something you cannot even remove with an anti-Hermitian omega. So there is something you can remove here with an anti-Hermitian omega as usual, but there is also something that you cannot remove. Fortunately, that goes away by itself, because the complete formula contains omega, which is the overall omega correction, but you see there is also omega in products, and these are omega corrections due to subdiagrams. Why? Because in this case, this as subdiagrams, consider for example this subdiagram. This subdiagram is the case of 2 adjacent propagators that we have studied earlier, this one. Since there are subdiagrams, you have to consider these 2 further corrections in the complete formula. And when you do it, you see that you finally get exactly what you want, namely the factorization between the 3 propagators. And you have the Feynman propagator for the physical particle and the purely virtual particles have principal values. You see how hard it is to get a simple formula, which is the one that you would write down immediately from the rules I gave 1 year ago in a different approach. In this approach, you need to struggle a little bit, but you always find the right answer. If you have only one purely virtual leg and two physical legs, the same procedure applies. Now, three adjacent propagators. If all of them have to be removed, proceed as before, overall omega, get the right result. If the third leg is physical, same thing, but also with subdiagrams. There is another surprise now. If you have two physical particles and the third one purely virtual, so let's say PV, pH, and pH. What is the surprise here? The surprise is that if you cut the two physical particles, you remain with a subdiagram here that is disconnected, yet you do need an omega for disconnected diagrams, which we will calculate in a moment. Once you do that, again, the corrections from these two terms, subdiagrams, and the overall correction lead you to the expected result. Even disconnected diagrams reserve surprises. Let's start from the product of a propagator times a vertex, a constant vertex with no legs. This is a propagator, phi times 1 times nothing. At omega equals 0, you still find not what you want, and you need a non-trivial anti-Hermitian correction to get rid of the rest. Once you do that, you get what you want. Then you can consider the product of a propagator times two constants, times two vertices that are just 1, equal to 1, with no legs. You get this. Again, you would say you proceed as before, but you cannot here because the correction you need to subtract is not anti-Hermitian. So it cannot be subtracted by the overall omega correction. It must disappear automatically by the omega corrections due to subdiagrams, which we saw before. And what are the subdiagrams here? The subdiagrams are precisely the ones we have considered earlier here, which indeed needed their own omega, because you can separate the two constants from one another. Once you do that, you find the right result. Then you can consider the product of two propagators, a simple disconnected diagram where you have the product of two propagators at omega equals 0. Again, you find many unwanted pieces, but you can subtract them with the same procedure. Let's move to something more interesting. Loop diagrams. Here I switch to skeleton diagrams because it's never necessary to integrate on the space components of the loop momenta. So I just integrate on the loop energies. Not only, but I simplify the propagators by multiplying them by twice the frequency. So this will be the propagator, this will be the conjugate propagator, and this will be the non-time ordered propagators. For example, an n polygon, which is the loop diagram with n internal legs, will be this product of vertices. K0 is the loop energy. I integrate on the loop energy and I do not integrate on the space components of the loop momentum. We will have to use this decomposition at some point of the fraction I divided by x plus I epsilon into the principal value plus the delta function, because the delta function gives the on-shell part, but we will have to use it only after integrating on the loop energies. And every decomposition of the diagrams will be made of these two ingredients. One is the on-shell part, which is the delta function with a pi, and I denote it by capital delta. And the other one is the principal value, which I denote by p. And then the q and p hat are just combinations of the same. But the basic two ingredients are these two, which are off-shell and on-shell. Let's see the bubble diagram. The bubble diagram in skeletons, after integrate on the loop energies, is just this. It's the sum of a principal value, p hat, it's just a principal value, and two delta functions. Oh, I was forgetting a detail. I insert an external momentum. A is the external energy of the leg A. I insert an external momentum for every internal leg, even if this is redundant, because there are not as many external momenta as independent external momenta as internal legs. This is always good, this is always okay, even if it is redundant, because there are always more internal legs than external momenta. So that's to keep in mind, because it makes the formulas much more symmetric and practical. Now, if you apply our reduction to the bubble, you will see the expected result when you project away both internal legs. You will find the expected result with omega equals 0. No need of omega. If you consider the square bubble with this interaction Lagrangian, you will find the square of this reduced bubble plus something else at omega equals 0, but that something else can be removed with an overall omega. So in the end you find the correct factorized result. If you consider the triangle, well, before considering the triangle, let's go to this paper that I wrote 1 year ago, where I decomposed the triangle in its on-shell and purely virtual parts, and this is the formula. This is the skeleton. So there are terms with no deltas, there are terms with 1 delta, and there are terms with 2 deltas. This is just the usual triangle with Feynman prescription. When you want to make the reduction, the projection, you don't just have the triangle, but you have corrections which are non-time ordered. If you apply that formula at omega equals 0, you do remove every single on-shell content, and you do get just principal values, and that means you have the purely virtual triangle. If only one internal leg must be removed, purely virtual, and the other two are physical, you still find the correct result right away by applying the formula we have started to study at omega equals 0. Everything is clean, direct, simple in the case of the triangle. You will never need any omega corrections to find agreement with that paper. And so this procedure produces the theory, the triangle of purely virtual particles, or mixed, some purely virtual particles and some physical particles. Box. The box has a different decomposition, of course, where you have a purely virtual part. You have terms with 1 delta, terms with 2 deltas, terms with 3 deltas. And this again you can find in that paper, and this is the Feynman skeleton. What happens if you apply the formula for the reduction with no omega when you want to remove all 4 legs? Again, you find the very simple result you expected. No omega needed. But when you have 2 adjacent physical legs and 2 adjacent to be removed legs, let's say, legs that carry particles that you want to remove from the physical spectrum, let's call them in advance purely virtual, but they are not yet, then you find a long formula which contains the right part plus something that you do not want. Again, that something that you do not want can be subtracted by means of an overall anti-Hermitian omega correction. So again, you can make the match with that. And these are, the square brackets here, in this case, I was too quick, they cannot be subtracted by means of an overall anti-Hermitian omega correction, because they are not anti-Hermitian. They are Hermitian. Luckily, they disappear by themselves, because we are in the case, let's repeat, 2 adjacent physical legs and 2 adjacent purely virtual legs. So the physical legs are 1 and 2. These are physical, 1 and 2. You see that when you cut them, 1 and 2, you have a subdiagram that is the subdiagram made by 2 purely virtual legs, and we already know that that subdiagram needed an omega. An overall omega for that subdiagram means a correction for the box. When you include that correction, which you cannot choose at this point, it's already given, you find the right result, in agreement with the other paper that passed here. If you have alternating physical purely virtual, then you do not have the problem. When the first 3 legs are physical and the last one is purely virtual, you obtain this long formula at omega equals 0. Again, this is no good, you have to get rid of it. And again, it disappears once you include the corrections due to subdiagrams. It cannot be removed by means of a new omega. It has to come from the subdiagrams, and you can check that correctly it comes the way you expect. And in the end, you find agreement with the formula of the other paper. Diagrams with more loops. This is interesting because there is a whole class of diagrams that are equivalent to 1 loop diagrams. For example, a stack of propagators with the same endpoints is equivalent to a single propagator. Consider this complicated diagram. This is always equivalent to a single propagator. And so in complicated diagrams like this, every stack can be replaced by a single propagator. And why is that? Because in skeletons, you have this identity that tells you that many propagators, the diagram with n propagators is equal to 1 propagator with energy equal to the sum of the energies and frequency equal to the sum of the frequencies. This is an identity that you can check, and it holds both for the time-ordered propagators and the Whiteman function, which is the non-time-ordered propagators. And so each stack is equivalent to a simple propagator, and this property holds through the projection and every formula we have written. The other case we consider is non-trivial, and it is a box with diagonal, because it can happen, in these kind of diagrams. So it's typical 2-loop diagram. It's the first and only non-trivial 2-loop diagrams you can build, with 4 vertices at most. Now, from the previous paper, this is has a complicated threshold decomposition. I do not want to get into details, but I just want to tell you that if you have every internal leg to be removed, then you directly find then you find this result, which is not in agreement with the one of my previous paper, because this would be the completely virtual, purely virtual box with diagonal, and that would have to stop here. This is the part where you only have principal values, just this. Then you have many corrections with deltas. Those have contributions of on shell, and if you want to remove them, you need to get rid of this. And you can get rid of it with an overall omega, but the important thing here is, why is there an overall omega? The reason is very simple. Take this, because here there is no subdiagram. Take the diagonal and contract it, you will see the double bubble. If you take the box with diagonal and contract the diagonal, you will see the double bubble, and the double bubble did need an overall omega. The two match, and you find a complete match by contraction. Okay, then you can check the other possibilities. In blue you have the physical legs, and in red the purely virtual ones, and here you don't need any correction. Here the same as above, here the same as above, but there is also one due to a subdiagram where you cut all the physical legs in blue. Okay, because that again in red you see you have the two adjacent propagators diagram. So we're getting to the conclusions quickly. What we have learned is that with omega equal to 0, the projection of a product diagram is not the product of the projected factors, but we can always find an omega that returns a factorized result, and the same happens when the diagram is not factorized or factorizable, but it factorizes under the contraction of some internal legs, as in the box with diagonal, which becomes the double bubble when you contract the diagonal. Such an omega must always exist, because the diagrammatics of my previous paper was a particular solution to the same problem we are trying to solve now in general, which was the problem of getting a unitary S matrix by projection from a unitary or pseudo-unitary S matrix. In some sense, this special omega is the one that minimizes the violation of time ordering, because it confines it to unfactorizable subdiagrams, which we may call prime diagrams, the factors. You can also develop interesting relations among diagrams to ascend and descend among them and among their threshold decompositions. I will not give you details, just tell you that the contraction is simply the limit of infinite masses. You first multiply by a mass and then take the limit, because the purely virtual part of a propagator tends to a constant and the on-shell part tends to 0, so you can separate the two by means of this projection, and you can check that all the formulas we have been given are related, from the hexagon to the pentagon to the box to the triangle to the bubble and to the tadpole. And the pentagon and hexagon have not given so far, but here they are. These are the purely virtual. This is the pentagon with 5 purely virtual particles. We can also ascend through the threshold decompositions by writing down the most general expression and then matching all the possible descents. To summarize, we have now a clear picture of the diagrammatics of physical and purely virtual particles. You know also what happens when we are so crazy not to use this special omega that implements the factorization, because in that case even something as simple as putting a propagator on an external leg or amputating the external leg requires to redo every calculation and a huge amount of effort. But all the corrections are given by cut diagrams, and that means that they all vanish identically below the thresholds. So they are corrections that start to be important only above the thresholds. In particular, they are symmetric under all symmetries you like, as long as the physical subspace you want to project to is physical, symmetric. So you don't need to worry about Lorentz invariance, about gauge invariance, about renormalizability. All these corrections, first, they do not change the renormalizability because they are on shell. So they cannot correct the overall divergence because they are on a compact support. They have deltas. And second, they cannot change the symmetries because all the operations of gluing diagrams together are perfectly symmetric and manifestly symmetric. Phenomenologically, this can be important if relatively light, purely virtual particles exist because they can change the phenomenology of physics beyond the standard model. You can check these papers for ideas and hints. But the most important thing is quantum gravity, because there using something new like this is not an option. You need to make a certain massive spin to particle purely virtual because it has the wrong sign in the kinetic in front of the kinetic term. And normally you have problems with unitarity because you use the Feynman prescription. But if you give up time ordering, then you have these new possibilities. Not only, but the theory that emerges by using this technique in quantum gravity is testable and gives a prediction. I go right away to the prediction and briefly tell you how to get it, and that's the conclusion. So this is the prediction. These are quantities that are familiar to people working in primordial cosmology. This is the tilt of the scalar spectrum. This is the tensor to scalar ratio, and this is the prediction. The tensor to scalar ratio, which is yet to be measured, is in between these two values. And hopefully in a few years, by Lightbird or others, we will know the actual value. You can find details in this paper. What is the theory leading to this prediction? It is higher derivative gravity, which is the Einstein term plus the Starobinsky term, plus a term with y squared that is necessary for renormalizability, but normally destroys unitarity. Now you can have unitarity in the projected subspace if you make the corresponding particle purely virtual. Now, to deal with cosmology is necessary to generalize the projection I've told you about to curved space. How can we do that? Well, luckily we can do it because if you are familiar with cosmology, at extreme sub-horizon scales and at extreme super-horizon scales, it becomes a free theory with an oscillator with constant frequency, and that's where we can use the projection as we normally, as we have done so far. And it is necessary to interpolate between the two, because in cosmology, I stress very clearly for those who are not familiar with it, it is not enough to deal with an effective theory to make predictions. Even if you make predictions about low energies, you need first to assess properly the high energy limit, like with the Bunch-Davies condition. And here, in addition, by checking that your unwanted particle is purely virtual there as well. So if you have a theory with ghosts, you cannot do anything. Strumia and colleagues, for example, have theories with ghosts and they think they can do everything. That's just false, because no matter how heavy the ghosts are, you need to properly assess the ultraviolet, in this case, before making predictions. And in the ultraviolet, no matter how heavy they are light. So you have them. But you don't have what I define as purely virtual. So the results are the following. Starobinsky inflation is the one. High energy physics privileges Starobinsky inflation. There is nothing else. Because this part does not change what happens in the background. It does change what happens to the fluctuations, but the mechanism is basically Starobinsky. Spectra and predictions are corrected as follows. These are the formulas corrected by the mass m chi and this bound, because as I told you, you can, yes, check, you have to check that your purely virtual particle is indeed purely virtual up to the ultraviolet, but that's not true in general. It's true only if this condition applies. And this is the key condition for the prediction. So, to summarize, if you use Starobinsky, you will have this prediction. This is an equality. Okay? Let me plot it So this is my prediction, is that the tensor to scalar ratio is in between these two values. These two values correspond to the two limiting masses. And if you have just Starobinsky, you would say it is here. If you have, so that would be the equality of this, 3. If you have theories with ghosts, Strumia, Salvio, and other Russian people, anything below that, anything. But if you have purely virtual particles, only this tiny window is allowed. So basically what I think will happen is that the first results will be a striking confirmation of the Starobinsky prediction, because at the beginning the error will be big enough not to know where we are precisely inside the window, but then we will also know the rest of the story, because the Starobinsky theory is non-renormalizable, so it cannot be the ultimate word. And the ultimate word will be that you are not sitting exactly on the upper extremum of this inequality, but a little bit below and within this tiny window. I review very briefly one transparency, the 3 equivalent formulations of purely virtual particles that have been worked out so far. The first one was a non-analytic Wick rotation introduced to get rid of ghosts with complex masses and reformulate the Lee-Wick models. And its ingredient is the so-called average continuation around the branch cuts of amplitudes, and you can find it in this paper. The second step was to realize that this procedure was actually leading to new models, completely different from the original Lee and Wick purpose. And they could also be used in the case of ghosts with real masses and physical particles to give sense of quantum gravity as a power counter renormalizable theory like the Standard Model. The second equivalent formulation was the one of 1 year ago, which we have compared today with a new one, where the diagrammatics is laid down in detail by means of the threshold decomposition of diagrams. And the third formulation is the one of this talk and this last paper. So the conclusions: we have formulated a new quantization principle for quantum field theory based on a special type of non-time ordered product, and shown that it gives the theories of physical and purely virtual particles. The diagrams of the physical amplitudes are built by means of the usual vertices and propagators plus non-time ordered propagators. The instruction to assemble the diagrams are encoded in a formula that maps the standard amplitude into the physical amplitude. If the usual amplitude obeys the unitarity or pseudo-unitarity equation, the most general reduced amplitude that obeys the unitarity equation depends on an arbitrary anti-Hermitian matrix omega. A special omega is determined by requiring that the projection of a product diagram is equal to the product of the projected factors, and that the factorization survives basic operations of ascent and descent through the diagrams. The idea is that time ordering should be violated in a sort of minimum way inside prime diagrams only. Then the amplitude, V omega, the physical amplitude, coincides with the amplitude of a theory of physical and purely virtual particles. Finally, in cosmology, what we have done lead to a sharp prediction for the tensor to scalar ratio R, and the remarkable thing is that this prediction is coming from the strong constraints of high energy physics. So it is essentially unique. There is no way out. There is only one inflation, that's the Starobinsky inflation, and there is only one value for R, and this is the prediction. Thank you.